Part 4, using a given zero to find remaining zeros. Theorem 2.7, conjugate pairs theorem. If f is a polynomial function with real number coefficients and a plus bi is a zero of f, then its complex conjugate a minus bi is also a zero of f. And this is always true. So if we have something like 3 plus 2i, and we know that is a zero of the function, then 3 minus 2i is also a zero of the function. Or if I have 5i is a zero, I know that negative 5i is also a zero of that same function. Recall that from a previous example, we had h of x equals 3x cubed minus 4x squared plus 2x, and we found that the zeros were 0, 2/3 plus square root of 2 over 3i, and 2/3 minus square root of 2 over 3i. These are the two complex conjugates. So any non-real number is going to have a complex conjugate also as the zero. Let's find all the complex zeros of this function. F of x equals x cubed minus x squared plus 4x minus 4. We can start by using our potential rational zeros, or we can notice that this function actually does factor by grouping. So let's do that. The first parentheses, I can factor out an x squared, and I get x minus 1. And the second parentheses, I can factor out a 4, and I get x minus 1. Now factor out the x minus 1, and I have x squared plus 4. So that's as far as it can be factored. X squared plus 4 cannot be factored further with real numbers, but I can find the complex zeros. So x squared plus 4 equals 0, then x squared equals negative 4, and x equals plus or minus the square root of negative 4, which is plus or minus 2i. So our zeros are 1, 2i, and negative 2i. Notice that 2i and negative 2i are complex conjugates, and they are both zeros of this function. Create a polynomial p of degree 3 with zeros x equals 3 and x equals 2 plus I that has real coefficients and leading coefficient of 1. So we have a 0 at x is 3 and at x is 2 plus I. So we know another 0 is x is 2 minus I, because that is the complex conjugate of 2 plus I. It tells us we want a degree 3 function. There's 3 zeros now, so we know that we're good there. And we have a leading coefficient of 1. So to write my polynomial, I know the leading coefficient is 1. And one factor is going to be x minus 3. Another factor would be x minus 2 plus I. And another factor is x minus 2 minus I. So each of the factors are x minus the 0. I can distribute through the inside parentheses on those second two parentheses, and I get x minus 2 minus I and x minus 2 plus I. And after this, it's a bunch of distributing. One thing I can do, if this makes it easier, is I can put parentheses around the x plus 2, and see here we have a difference of squares. So I have x minus 3 times x minus 2 squared minus I squared, which would be x minus 3 times x squared minus 4x plus 4 plus 1. Negative I squared would be negative 1, which is positive 1. So x minus 3 times x squared minus 4x plus 5. And now we'll distribute the x minus 3 through that second parentheses, and we get x cubed minus 4x squared plus 5x minus 3x squared plus 12x minus 15. And then combine our like terms, and we have x cubed minus 7x squared plus 17x minus 15. So here is our polynomial function, degree 3, zeros at 3, 2 plus I, and 2 minus I, and the leading coefficient is 1. Let's do one more example. Create a polynomial p of degree 4 with real number coefficients that has zeros negative I, 2, and negative 2. So the non-real number there is negative I, so x equals positive I will be another 0. So to create this polynomial, we know we have a leading coefficient. We don't know what it is. We'll have to use the p of 3 equals 25 to figure out the leading coefficient at the end. And then each of my factors, I have x minus I, x minus the negative I, x minus 2, and x minus a negative 2. So x minus each of the zeros, and then I need to distribute x minus I and x plus I, that is a square or difference of squares, so I have x squared minus I squared, or x squared plus 1. And x minus 2 and x plus 2 is a difference of squares, so I have x squared minus 4. So a times, if I distribute here, I have x to the 4th minus 4x squared plus x squared minus 4. And combining my like terms, I have a times x to the 4th minus 3x squared minus 4. So there's a polynomial. I don't yet know what the leading coefficient is, but I do know that p of 3 equals 25. So p of 3 is a times 3 to the 4th minus 3 times 3 squared minus 4. And we know that has to equal 25. So a times 81 minus 27 minus 4 equals 25. And 81 minus 27 minus 4 is 50. So a times 50 is 25. Divide both sides by 50. And I get a equals 1/2. So my polynomial with that leading coefficient now is 1/2 times x to the 4th minus 3x squared minus 4. And if you want to distribute that 1/2 through the parentheses, you would get 1/2 x to the 4th minus 3/2 x squared minus 2.